Get started. So today, there's only one of two things I want to do. The first thing I want to do is to answer all your questions. Since last week we have our first week of remote online or virtual classes. So here today, I just kind of want to answer some of your questions about, some of the questions you might have. And then the second thing I want to do is to have you guys to work on some of the surveys. I think the survey is not my survey; it's a survey for other professors. So we would take 20 minutes to complete that. And then the last part is where I want to go over the last part of the recursive recursion, the recurrence relation, because I remember that I stopped at one example, so I will go over a couple more examples so we can talk more about recurrence relations and how we solve, um, or how we analyze algorithms that are recursive in nature. Um, so I guess first thing first, any questions from you guys, from any of you about this class, anything, or from yeah.
For the main homework problem, how do you want to submit the test cases?
You can just code it inside. I mean, you can. I mean, as long as I can see it. I mean, so basically, if I can see you test certain things exhaustively, then you're fine.
Okay.
You can hot code it inside. You can have different testing unit that you want to do. It's okay with me. I typically when I grade this, I look over people's code. But I actually look at your code, not just submit to online stuff. So I read your syntax and read how you program stuff and how you do your logics. So again, this class is not programming. Like this is different from your previous CS1 or CS2. This class is more about solving problems. So what I'm focusing on is more of your algorithmic thinking, how you develop algorithms for tackling problems. So this class is more about problem solving, not about programming. Again, if you do okay with programming, it's fine. I don't pick on you in terms of how you define your variables and how you set your names and things of that nature. So I'm caring more about your algorithmic process, right? How you think about how to solve these problems and how you implement these sort of things in terms of algorithm. Okay. Again, I just want to show you the classwork page. Hopefully, most of you already looked at this. I didn't connect that was a nervous first week of personal class. I don't know why it's working earlier. So weird. I know they've been having issues in in this machine, or I guess in with the projector this morning, but I came in like earlier and it didn't have any. I didn't have any problem with it. So weird. Okay, it works now. Apparently, after I tried a few times, it works. So anyway, so this is the classwork page. Hopefully, you have looked through it a few times. Homework again will be posted here. Homework 1. So I already list a few homework questions. You should be able to take a look. I think most of them you should be able to do either from the class from the lecture, based on the lecture that we talked about, or based on your knowledge from your previous classes. if you don't, let me know. We can talk about this. There are some algorithmic puzzles I put in there sometimes. So quite often I like to give you puzzles to think about. A lot of these puzzles would be connected to the concepts that we talk about in class. I think it'd be fun to solve. It'd be also interesting to think about for you, for most of you, or hopefully all of you. Any questions for this so far? So again, if you have any questions, let me know, and I will try to answer it through email or in person. What else? Any other questions? Tests and final. So there will be 2 tests in this class, midterm and final. I've been thinking about this over the last few weeks, and I have decided to have and take-home final and midterm. I think that would be more reasonable for some of you that would like to take it home or would like to work on it in a more comfortable environment. And also, it would be a backup plan in case we have to move the class entirely online in the future. So I think that's the best policy or the best possible way that outcome, I guess, was. So having said that, I will kind of handcraft some of these questions, just so that just to test the question, to test the knowledge and other things. So another thing that I usually like to do is to have this programming contest. So like near after midterm of the class, but I don't know how we want to do this year because usually what I have done is to have people come in and I gave you like a set of problem set and you group together you have a team of 3 to 4 people and then you work on these contests together or program contests together and you get bonus point. But in this case, I need to think about what we can do about this. I mean, yeah, maybe we want to just move this whole thing entirely online, or but we have to think about other alternatives if we want to do this. In terms of group projects, so usually I have students do group projects. Group projects from last semester is where I have people or a group of students come in, maybe a team of 2, that present a chapter of the book, and they went to implementation and also coding part of the assignments and demonstrate that they know they can teach a class and also they know the concept of some of the materials in the book. So that's something that I can talk about later on throughout the semester, but just be aware of that. And at the end of the semester, I will have some of you to present your class projects. Again, this project will be covering some algorithmic problems or idea, or particularly some chapters in the book or some external reading. I kind of encourage you to meet with me in person to talk about what you like to do. But again, you can think about it as a class progression. That's all. Again, so homework 1 would do on the 31st, so we have one more week for the homework. So that's that one. So having said this, I want to switch gear a little bit if you don't have any more questions. I want to talk about a plan for the day. In particular, I have to keep moving some of the stuff. Okay, so today as I said, I want to cover the last part of the recursion. But before that, I want you to take maybe 20 minutes to take the survey. If you have a computer, it's good for you to take it out. and go to this link. Again, this is not my survey. This is a survey that conducted throughout the years by two professors in our department that conduct educational research. So I mean, here we just try to help them out and try to provide responses. Again, like these will be anonymous. You're not going to be, it's not going to be, your information is not going to be recorded. I mean, I guess we're not going to know your identity, anonymous. So feel free to work on these survey maps. I guess if you're online watching this, you might want to skip like 20 to 25 minutes later once you hear like a long pause. But I'm just saying to the camera so that they don't keep watching. Nothing really happening. So can you guys or one of you tell me what we did last time, like last class? Just recall what we talked about from the last lecture. Yeah.
We talked about analyzing time efficiency for recursive algorithms.
We also talked about non-recursive algorithm, and we kind of stopped here, right? Today I want to go over a few more examples about this. Non-recursive algorithms. If you don't have example, if you have any questions about non-recursive algorithms, let me know right now. I mean, so we went over some examples, right, in the presentation, right, and then we talked about input size and the time complexity for particular algorithms, and we look at how we can measure time complexity using summations and recursion. And we talk about some examples, and here are some of the useful identities you can use. In the back of the book in Predict8. I hope that you're able to find the PDF copy of the book. Most of you, if you know, let me know. And then we went over a couple of examples. We worked with some summations, and we sort of discussed, how we count the number of basic operations in some of these examples, and we ended up deriving that in some of these examples, the running time of some of these examples, right, using summations. And in recursions, we sort of let me just skip all that. So in recursion, we went over one example, right? So we talk about this algorithm. Right? Do you guys remember what this is? Which is factorial, right? Something that you've done before. And we say that the input is value of n. The input size is the number of bits we need to represent the particular value n, right? And then we look at the complexities and we say it's n, but in reality it's big O 2 to the b because we need b as number of bit represent the input size, right? So a lot of time when you want to look at algorithms, the key emphasis is that you want to represent the running time of your algorithms with respect to the representation size. And the representation size here is the bit, so we need to do the conversion right into the bit. So the running time is really regular to the once we do that. Now we went over some examples last time, right? And we used it as an example about how to analyze this more concretely, right? And we talked about setting a recursion m, right? M is the number of time this modification is executed in this code, right? And then we look at base cases where you don't have zero element, n equal to 0, and then you don't do any multiplication operations. And then we went over how we solved this in the slide by doing repeated substitutions. And essentially what's going to happen in that we're going to do repeated substitutions, and then we're going to substitute in n where we achieve the base case, and we have this number of times this algorithm is end up running. Any questions? Okay. So today I want to go over the second examples. How many of you heard about this game, the Tower of Hanoi? Okay. How many of you actually play this? So we're going to try to play this, and we try to count the number of time we need to move one. Oh, so okay. For those of you that don't know about this, so the problem is that you have a bunch of disks, right? That you arrange them from the smallest disk to the largest disk to the smallest disk, and it goes to move all the disks from here to this pile, right? Using this one as intermediate pile, and you want to achieve the same ordering where the largest disk is at the bottom, and the smallest disk will be on the top. Right. And when you move this pile, you can only move one pieces at a time, and you have a condition where the smallest piece is always going to be on top of the bigger piece. And the question here is, how many times do we need in order to move this pile of this into the last bit? So that's the questions that we try to answer. And it turns out that we can solve this using recursion, but before that, I want you to think about how we can play this, or just do some examples and how we can, we do this for very small cases. So in this case, what should we do in order to get to the last disk?
So you go like all the way to the right.
This one?
Yeah.
Move this all the way to
Yeah, and then you go to the middle. Just the left
this one.
Yeah, the middle. And you go right to middle. Left all the way to right. And then left to the middle.
To the left.
Right.
Right. So we have minimum move of 7, and this is the correct answer. Now what happens if we go to the fourth disk? You want to try that?
Sure.
Okay.
Put the small one in the middle,
Small one.
and then the next one to the right. Small one on top of that, and then the third one in the middle. Small one all the way to the left, and then that one in the middle, the small one in the middle, and then the big one on the right, and then the small one on the right.
On the right.
And then that one to the left, the very small one to the left, and then the middle one to the right, small one in the middle, and then that one all the way to the right, and then the small one.
Okay, great. Okay. So these are not that hard. Well, I mean, for small cases, it's gonna be relatively easy to solve. But once you move up higher, then it's gonna be a bit more complex, right? So the question here is, how do they actually getting these values at the end? How do you determine the minimum number of moves you need to make in order to move from one pile of this from the left hand side from any number of this to the stuff on the right hand side, right? So that's the goal we're trying to achieve. So it turns out that we can analyze this using recursions, and let's go back and analyze the moves that we just made, and then we're gonna try to come up with a recursion with transform relations in order to count the number of times we need in order to move this pile of this to the one to the right. Yeah, sorry, I have to switch back and forth just for those people that want to watch this online. I don't know why I just keep doing this. I think I clicked on the wrong thing. So how do I swap this one back again? So I need to click on. Okay, so go back to the cases that we looked at. So what is the idea here? Well, the idea here is that we want to move so the idea, what was the idea? So the idea is this: we move. So we start from this initial position, right? What we're gonna do here is that we're gonna move to this from take 1 to take 2, right? Using 3 as intermediate, right? And then we end up moving this guy to the largest one here, or to the one on the right hand side. And now we move the rest of the disk here to the one on the right hand side using the middle or the leftmost one as intermediate. And for this 4, we use similar reasoning, right? So the idea is that we first move 3 disks from the first peg, right, to the second peg, right? And then we move the largest one on the bottom to the one on the right hand side. And then we want to keep doing that until we have everything to the left. So here, the similar idea gives very simple recurrence that sort of allow us to understand what we need to do in order to count the number of operations that we want to perform. In particularly, the idea is that we can do this recursively. If you let n to be the number of times you need to move from peg 1 to peg 3, we can write down recurrence relations where m of m is the number of times, right, that we want to count, which is based on the number of times you need to move the n minus 1 disk from the first one to the middle, right? And then once we move the n minus 1 disk to the middle, then we can move this one disk to the one on the right hand side, which gives additional operation of 1. And now we need to add on the number of times we need to move the rest of the disk, right? Of the n minus 2 from this pile to the right pile. Does that make sense? Does that make sense? So again, n minus 1, this m of n minus 1 is the initial operations where you need to move the disk here to the disk to the second pile, right? The 1 here denotes the number of operations you move from the largest disk here to the last peg, right? And finally, the n minus 1 is basically what is the remaining operation we need to do to move the last pile to the one on the right. So this is a recurrent relation. What are we missing here?
You need the base case.
Yeah, so base case. So what would be the base case here? What would be the right base case?
Probably moving 1,
Mm-hmm.
maybe 2.
How many say 1? How many say 2? So, okay, so if the base case is 1, what is the value of 1? Or moving 1? Right, just 1, right? So now we have this recurrence relation, and we can solve this directly. So the question is, how do we solve this recurrence relation? Now, so we have this relation. M of m is equal to 2 to the n. M of 1. So we're going to try to solve this with initial conditions of n1 to n. I think you have done this in your homework for 235, something similar. Maybe. So we're gonna try to expand this term, right? We're gonna substitute n minus 2, n minus 1 here, so we get n minus 2. So we have 2 times 2 of n minus 2, right, plus 1. Because I'm substituting this n minus 1 here, I'm getting 2 times m of n minus 2 plus 1, which is what I have here, right? Plus 1. Right? This plus 1 comes from this. And we're going to keep substituting until we see a particular pattern that we see, right? And then we substitute in the base case of n in which we have this particular value of 1. So now what happens when we substitute this guy in again? So we have 2 times this we have 2n minus 3 plus 1 plus 1 plus 1. So if we're gonna divide our simplify everything, and we have minus 3 plus 2 to the square, right? So we got plus 2 plus 1. So you're going to keep doing this. You're going to get a term something like 2 to the I, m of n minus I, plus 2 to the I minus 1, plus 2 to the I minus 2 plus 2 plus 1. So this part, we're going to use a formula that we know before. I'm going to try to go through this. So I think you have seen this formula from your class, your previous classes. Have you seen this identity where the top part is the sum of I equal to 0 to n, right? And then you have 2 to the I is equal to 2 to the n plus 1 minus 1. So we're going to use this identity, right, on this side. So what do we have here? We have, so n is equivalent to this I here, right? So we are summing up. Well, I mean, the index C is different, so maybe you want to think about it as I instead of j, so that you can substitute in this I minus 1 here. Right, so you get you get 2 to the n, or so you get 2 to the I minus 1. So you have 2 to the I and minus I plus 2 to the I minus 1. So now we're going to substitute in the base case. So the base case is 1. So we're going to let I be n minus 1 so that we get the base case here. Right? So when you substitute in the base case, you have 2 to the n minus 1, m of 1, because when you do minus I, then this term cancels out, and you have 1 of those. And then you have plus 2 to the n minus 1 minus 1. So you have, so this part is 1. So you have 2 to the n minus 1 plus 2 to the n minus 1 minus 1. And then this part becomes 2 to the n plus minus 1. Right? Because you factor out, so you have 2 of these guys, right? So you have 2 times 2 to the minus 1. So 1 cancel out. Is it clear here? How I go from here to here? Can you guys see back there? I'm sorry, if you can't see. Is it hard to see? No. So at the end of the day, this is what we have, right? You have 2 to the n minus 1. Do you think this is correct? Let's check, right? Because last time we say that when n is equal to 3, the answer is 7. So we have 2 to the third minus 1, which is 7. N equal to 4. I don't remember what they say there, but based on this formula, you have roughly or exactly 15. So this is a formula for the number of time you need to move from n theta from the left all the way to the right. Okay. I think I also have put up the math online too, just so that some of you, if you want to look at it, is also online too. I tend to like to do this in person because it feels a bit, I guess, close to me. Like if you can manipulate the math by hand, then usually it feels a bit better. Because I remember when I was undergrad, before we have all these, when I was taking math classes, a lot of time professor would draw a lot of these things on the board, and then we do a lot of stuff by hand. But nowadays, a lot of these is online. But anyway, so you can follow this. It's the same duration. I mean, it's what I have here. But this is just a repeated version that I did. Now, here's another example. I want you to take some time to think about the number of time division is executed in this algorithms, and see if you can find a recurrence relations for this. So suppose that we have this algorithm, and every time in the recurrence relation, or in this recursive algorithms, we gotta divide n by 2. We're gonna keep dividing it until we have 1 at the end. And the question is, how many times division is executed? So what would be the recurrence relation for this one? I'm erasing this. Is that okay? So the question here is, what a n should be? What is the recurrence relation? Any idea? So it turns out that this thing inside is halving your problem instance by 2, right, every time. So your recurrence relations is sort of naturally follow a very similar formula, which is this. And the question is, what is the number of operations it's performing, right, after you're halving it? Also, if you're counting the number of divisions, then it's only it's only one, right? One part. So it'd be like this one. Again, if you don't know how to construct this, it's okay because we're gonna go over that later on in the class. But I'm just explaining to you using this example to demonstrate we can construct a recurrence relations out of this in solving for this running time. And the base case would be
A of 1 equals 0.
yeah, A of 1 is 0, right? Because we don't do anything. Yeah, sorry. Now, how do we go about solving this? So a lot of the time, what people usually do here is that we can assume that n is a power of 2, n is equal to 2k. So if you see like homework assignments or questions like this, you can assume that n is some power of 2k, and then solve this recurrence relation based on this. So this is, so we can use, so if we substitute in this in the 2k, then we have this 2k minus 1 plus 1. And the question is, how do we go about solving this? So we can do the same thing, right? So we can say a of 2 of k minus minus 2 plus 1 plus 1. Then we can say, and then you can see the pattern, and you can say a of 2 of k plus k. Now this part is 0, so we have this recurrence is equal to k. Now we're not exactly finished, right? Because we want to count the number of times the n is running, right? So we need to convert this thing back to n. So we need to convert. I'm just blocking my goal. So we need to convert this back to n. So how do we convert this back to n? So we solve for n. So now, so to convert this with back to n, we have 2 to the k equal to n. So we take the log of both sides. So we have k of log of base 2 of n. So you take the log of base 2. Yes.
On the screen it says if n equals 1, return 1. And on yours you have the base case of 0.
So it depends on the number of basic operation we're counting. So the basic operation we're counting is division. When n is equal to 1, we're not doing any division. So a lot of time you have to think about what will be the basic operations of the algorithm to be. Because sometimes in the base case you don't do anything, right? Then that would be so again, the key part when you analyze an algorithm is to identify basic operations, the most expensive operations. It could be division, it could be addition, it could be multiplication, it could be comparison. And your recurrence relations will be based on the most basic operation. Cool. So the question is this, are we done? I mean, I think a lot of times the book kind of finish off here because this will be your number of time your operation actually happening. Now, what happened to the running time? Like, what is the actual running time of this? So we know that this a of n is equal to log of n. But the question here is, what is the running time at the end of the day? You have to think about the input size, right? How do you represent the input size here?
That's a
Binary bit, right? So now, essentially what's going to happen is that you have to convert it again, right? This is log of 2 of n. Right? So you have to convert this this would be 2 of B, and this would be 2, right? So it turns out that the running time of this algorithm is actually B, which is good news because it's linear with respect to the representation size. I don't think the book talked about this too much. I just wanted to highlight a little bit so that you can feel aware of this later on in the future. Anyway, so you will, if you don't, so the only thing, the takeaway today is how you solve a recurrent relation. I will give you a few homework problems to do that. Analyzing it, you will learn throughout the course, but I'm just showing you some examples. Again, I'll have some of the math online. You can follow this also. You don't have to write it down. The last thing that I want to talk about is some of the resources here. I think it's in the appendix. So you might want to look at the identity if you get stuck or manipulate some of these mathematical formula and doing substitutions. I think the key part a lot of time will be 2. I will use 2 often. Maybe I will use some of these identity. Again, you feel free to look at it. And also resource 2 would be also some of the formula, summation formula. I think the most popular one will be the first one, the second one, and then maybe the 5th one. So they're mostly commonly used, at least in the class here. I mean, we don't kind of use the other identity as much, but they're good to know. Did I went over? Yeah, sorry, I went over it a little bit. But that's all I have for today. And then I will upload the PowerPoint online, and then you